Okay, we're going to do experiment 16, simple harmonic motion. Now, this is going to look a lot like one we've done before, the potential energy of a spring, but it is a little bit different. We just completed the chapter 15 module, or you should complete it soon, the chapter 15 module on simple harmonic motion. So we're doing an experiment uh, with simple harmonic motion. We're going to start by doing a one we've done before, where we get the spring constant K via stretching a spring with masses and uh, and seeing how much the spring elongates, and plotting the force versus the elongation. Um, but then we're gonna set this the spring into oscillation mode, which I think we did that in the past. But we were looking for the potential energy. We would look to see how high the spring would rise uh, with the mass, and we were plotting potential energy. Here, we're actually going to look at the oscillation. That's what we're studying. We're studying simple harmonic motion, and this back and forth motion is simple harmonic motion of the spring pendulum. So it's going to feel like an experiment we've done in the past, but it is a little bit different. And um, so we're going to go through the experiment here. Simple harmonic motion. Here's the advanced study assignment. You answer those questions. There is a section. Um, of course, we're doing the TI. We're not doing the CI, but you can, if you want to answer the CI questions, the advanced study assignment CI, I'll give you extra points for that. You're not required to. No points will be deducted if you don't do it. But here, this is we've seen this before. We've seen Hooke's law before. Force is equal to minus kx, where k is the spring constant, and it's minus because the force is always in the opposite direction of the displacement. And K is the spring constant. The spring constant is sometimes called the stiffness constant. It's highlighted here in red. It gives an indication of the relative stiffness of a spring. The greater K, the greater the stiffness. So if you have a real stiff spring with a high K, it's harder to stretch. Of course, you have the elastic limit that we've discussed in the past. And I don't remember if this is in the last one, and this is on page 229. There's an error. It's a simple error, but they forgot the slope right here. You can see. Let me change colors here. This M, they forgot it. Y equals mx plus b. It's of that form. They didn't include that in your text. I don't want it to confuse anyone. Okay, so we're going to use this. Let's read this highlighted part here. Y is equal to a cosine 2 pi 2 pi over t, capital T, which is the period, times t, which is the time. Now this is the same. 2 pi divided by t, the period, is also equal to 2 pi f, which is known as omega. 2 pi f is omega. So this is the y equals a cosine. This is the same as y equals a cosine omega t. That doesn't look like an omega, but we'll try to make it an omega. A cosine omega t, which is we've already discussed that in this experiment. In actual practice, the amplitude decreases slowly as energy is lost to friction, and the oscillatory motion is slowly damped. I'm reading here on this section. Now, in the simulated experiment that we're using, we can take away damping, so we can idealize the situation. And we're going to use this equation TI 16.3. T is equal to 2 pi, the square root of the mass divided by the spring constant. So we're going to come up with the spring constant two ways. The first way is by stretching it and seeing the elongation. And the next, we're going to measure the period. And if we solve for K, we'll get, we can get the spring constant that way. Now, we're gonna skip part A. I've got it scratched out here, the rubber band elongation. The there, I don't have a simulation where the where we use a rubber band instead of a spring. And basically, this part of the experiment was to show you that rubber bands don't obey Hooke's law. They're not a good uh, representation of Hooke's law, and that's all it was really meant to show you. So we're gonna skip it. We are gonna do the spring elongation. It's one we've done before, where you just put a mass, and see how the spring elongates. Then we're gonna set it into motion. We're gonna put it into motion, and using a laboratory timer. There'll be a stopwatch available on the simulator where you're going to use the fet.colorado.edu simulation. Once again, using the laboratory timer or stopwatch, release the spring weight hanger from the predetermined initial displacement and determine the time it takes for the mass to make a number 5 to 10 complete oscillations or cycles. I prefer 10 because if you use 10, you just move a decimal place from whatever you got on the timer, and you'll get your period. So if we when we first do a light mass, it might take 9 seconds to count to 10 oscillations. Well, 0.9 seconds. The period is 0.9 seconds. If if you go to a higher weight, a higher mass, and it takes 20 seconds to count 10, well, then you've got a 2-second period. So it's real easy to count 10 and get the period that way. So then you want to plot a graph of the average period squared. You're going to square the period versus the mass and draw a straight line that best fits the data points. Determine the slope of the line and compute the spring constant K. So you're going to be able to get the spring constant. Now notice here, I'm blowing it up real big because it's this part of the equation. This is what you're going to use. I know I'm going to get questions from students. Well, how do you use the slope to find the K? Well, here it is. K is equal to 2 pi squared divided by the slope. Whatever the slope you get, the slope is that you get from plotting T squared versus the mass, you put that slope into this equation and you'll get your K. K is equal to 2 pi squared divided by the slope. So you put T squared on the vertical and mass on the horizontal. And now I don't want anybody reproducing this data. Your data should look different. Again, we don't do data table 1. You're gonna populate data table 2. This is just the stretching, and then you plot out. This is mass. Actually, you want it in newtons. Mg divided. Mg on the vertical and displacement on the horizontal, and that mass will give you the slope of the graph. I've got it right here. You'll get the slope of the graph just from plotting the elongation, the mass versus elongation. Then you're going to suspend some masses. You're going to get the total time. I did 3 of them and got an average. This is old data. Again, I don't want anybody using this data. You're going to require your own data. Number of oscillations I used was 10, and you're going to get an average period. I told you about 0.9 for 100 grams. and you square that, you'll get t squared. When you plot t squared versus the mass, you're going to get a slope of a line. And if you use that equation that we saw here, you can get your k. K is equal to 2 pi squared divided by the slope. And I think that's pretty much all that's required. And then you just answer the questions. Okay, I will run through parts B and C. Let's see, I'll run through parts B and C, give you the link for uh, the FET site that I want you to use, and you'll perform the experiment yourself virtually. All right.